So from chapter 4 also, when I discussed excess carriers, you had an idea that uh, interaction of semiconductor with photon is a actually important aspect of semiconductor devices, right? When photon semiconductors interact with photon, optically generated carriers, excess carriers may be there, and those excess carriers modify the conductivity of the semiconductor, that really increase the conductivity, and that in some cases that phenomena can be used for some applications. There are also some other applications. So the main thing is interaction of semiconductor device with photons, that is important. Okay, so there is a class of device actually which a semiconductor device which operate on this principle, interaction with photon. Those are optoelectronic devices. Okay, so that is the beginning of this chapter 8 of electronic devices. There is also a variety of very interesting and useful device functions involving the interaction of photons with semiconductors. These devices provide the optical source and detectors that allow broadband telecommunication and data transmission over optical fibers. This important area of device application is called optoelectronics. So probably you have heard of optical fibers. Nowadays, the internet infrastructure is actually almost 100% based on optical fiber communication. Okay, there are thousands of kilometers of optical fiber lines connecting all the continents of the world, and the internet traffic mostly goes through this optical fiber network. Okay, in previous days, VSAT used to be used, which used actually satellite communication for internet, but nowadays VSAT is almost obsolete. No one uses it. So in optical fiber, actually data is transmitted through by using optical signal, light. Okay, but the data is actually electrical in nature. You know that uh, the data is actually nothing but voltage in digital transmission. Actually nowadays all the transmission is digital, so digital, you have idea, is represented by two states of voltage: high voltage, low voltage, right? So data is voltage, but the carrier is light, so somehow you have to uh, convert your electrical data into optical signal. Okay, so in from that perspective, this optoelectronic devices come handy. Okay, these becomes useful. And in this type of applications, optical source is required. Optical source means you have to generate the light somehow, which you will be sending. And also detector is required at the receiver side, where you detect the light, and from by detecting that light you extract the data from that light. Okay, so optical source and detectors are very important in this type of communications. And these things have to be can be made using semiconductor devices, because semiconductor devices can interact with photons. Okay, so these branch of semiconductor devices, this is called optoelectronics. We'll start with a general discussion. Photodiode uh, is nothing but a diode which interacts with photon. Okay, so we saw that. Let's see it. We saw that the bulk semiconductor samples can be used as a photoconductors by providing a change in photoconductivity proportional to an optical generation rate, which I discussed before meet. Okay, photoconductors. Often, junction devices can be used to improve the speed of response and sensitivity of the detectors of optical or high energy radiation. So, junction devices means PN junction. Okay, for optoelectronic application, many application, uh, PN junctions are used. There are some advantages of using PN junction, which some idea is given here. The speed of response is better and the sensitivity is better if we use PN junctions for optoelectronics. So two terminal devices designed to respond to photon absorption are called photodiodes. So photodiodes are two terminal devices. You can understand from the name, it is a diode which responds to photon. That's why photodiode. Okay, so photodiode is actually general term. There are different applications of photodiode. Photodiodes can be used for different applications. This is a general term. We will see about those. What are the different applications in the following chapter, for the following article. So next article is current and voltage in an illuminated junction. So here you can understand that we photodiode, we have a diode which will interact with photons. So you have to supply the photons. So the PN junction has to be illuminated, right? You are supplying light to the PN junction. When you do that, what happens? That is the topic of this article. So in chapter 5, we identified the current due to drift of minority carriers across a junction as a generation current. Remember that? In junction, we talked about four components of current: hole diffusion current, hole drift current, electron diffusion current, electron drift current. Diffusion current component of the current flows from P to N side, right?
Yes, sir.
These things I told you, you have to remember these things. You cannot forget these things. So P to N, diffusion component. Drift component flows from N to P, and the drift component results from the thermal generation of carriers, right?
Hmm. Yes, sir.
Yes, sir.
Interesting.
So the diode equation, you remember diode equation I contains two terms. First term e to the power qv, I0 into e to the power qv by kt minus 1. Remember that equation?
Yes, sir.
Yes, sir.
So first term is the diffusion component, I0 e to the power qv by kt. That is the diffusion component, minus I0. That I0 is drift component, right? So
Yes, sir.
in that equation, it has been assumed that I, total diode current, I is from P to N, right?
Yes, sir.
Yes, sir.
This equation, I equal to this, here I thermal is actually I0. So this component is from, this is the diffusion component, which is from P to N. So here we have assumed that forward voltage is forward voltage. This is diffusion component, and this is drift component. So diffusion component flows from P to N, drift component flows from N to P. That's why this is minus, reverse direction, right?
Yes, sir.
So this I is forward current from P to N. But this is a general equation. We can apply this also for reverse bias. In that case, this V becomes negative, and this first part becomes actually almost negligible, almost zero. So I becomes minus I0, or I thermal in this case, same thing. So minus I0 means what? From N to P. Direction is from N to P. So P to N direction has been considered as positive, and positive uh, on P side, negative on N side. That polarity of voltage V has been considered forward voltage, forward polarity of the voltage, right? In
Yes,
the
sir.
equation. So these things will be required actually. So in particular, in particular, carriers generated within the depletion region W are separated by the junction field, electrons being collected in the N regions and hole in the P region. So in order to explain this, actually, it's better if I show you the diagram, the zoomed in this diagram. This is a PN junction, right? Illuminated PN junction. These are photons, and these photons have energy greater than Eg. Why greater than Eg?
Because conduction band যাইতে হলে স্যার ভ্যালেন্স ব্যান্ড টু
From
কন্ডাকশন ব্যান্ড
electrons from valence band must have to go to conduction band. Otherwise, there will be no interaction with photons, right?
yes sir
So in the depletion region, P side has negatively ionized acceptor ions, and N side has positively ionized
ডোনার
donor ions. So because of the um, illumination, there will be, this illumination is uniform everywhere. Same number of photons are falling per second, and this is a steady state illumination. So when there is a steady state illumination, in chapter 4, probably you remember, there is a steady state generation rate, GOP, optical generation rate, which is related to
Carrier lifetime.
recombination lifetime,
Yes.
right?
Yes, sir.
Remember that.
Yes, sir. A divided by A naught plus A naught.
So because of this optical energy in this depletion region, carriers will be generated, EHPs will be generated, right? Now these EHPs, the electrons when because of this electric field, the electrons which will be generated here, those electrons will go to which side?
Yes, sir. Those electrons will go to N. The direction will be from N to P. Electron will go from to the N side, but the current direction will be from
Exactly. Electrons will go to N side
N side, but current direction will
because
be
of this field, right?
yes, sir.
And the holes also, there will be holes. The
Yes,
holes
sir.
will go to the
P side.
P side. So uh, corresponding to this movement of electron and hole, there will be a current, right?
Yes, sir.
Holes moving in this side means current is also from N to P,
Yes, sir.
right? Electrons moving to this side means current
Current
is
from
from N to P. So for both type of carrier movement, current is from N to P. And this current is current generated due to optical absorption, photo generated current, you can say. So the photo generated current has a direction same as the drift component of current, right?
yes, sir.
Okay. Other than this, there will be also carriers generated uh, within one diffusion length of this edge. Remember, this is XPO, this is XNO, right?
Yes, sir.
So from these edges, from XPO to one diffusion length, within one diffusion length, LN,
Mm.
uh, also there will be carriers generated. Carriers actually will be generated everywhere.
Yes, yes.
But those carriers which are generated within one diffusion length, they have the possibility they can diffuse to this, not they actually, from here electrons can diffuse here, and once electrons diffuse here, those electrons will be forced to go to the N side by this field.
Yes,
Okay.
sir.
But electrons or EHP, electrons actually EHPs will be generated, but only electrons will can diffuse because there is barrier here. For positive
Drift.
charge, there is a barrier here. Holes cannot go here. So electrons which are generated far from this edge, before they come to this edge, they will decombine, because what is the definition of diffusion length? Diffusion length is the average length through which a carrier can diffuse before recombining. Okay.
Yes, sir.
So within one diffusion length, the carriers which are generated, they may go to this depletion layer, but the carriers which are generated far further away from this edge, they will not be able to diffuse. The electrons will not be able to diffuse here. Okay, so we will not consider those electrons. Similarly here, from XNO within one diffusion length, on diffusion length for holes, of course, not electrons. Electrons cannot go from N side to P side because of these barriers. So holes will generated here within one diffusion length. They may diffuse here, and once they diffuse here, they will be forced by this to go to this side. So again, similarly, current will be from N to P. Now these holes, the holes which are generated further away from the edge, they cannot diffuse here because before they reach this diffusion layer, they will recombine. Okay. So in total, contribution from three regions will come to the optically generated current. One contribution will come from the carriers generated within this W. So if the cross-sectional area of this PN junction is say capital A, the volume of this region is A into W, right?
Yes, sir.
And another contribution of carriers will come from this region within one diffusion length of P region Ln. So the volume of that region is A into Ln, right?
Yes, sir.
And similarly, another contribution will come from here, here
Yes,
holes, and that will be ALP.
LP.
That volume will be ALP. So this part understood.
Yes, sir.
So you, by considering these three regions, we can get the equation of optically generated current or photo generated current. So let's go back to our discussion here. Those things actually are mentioned here. So in particular, carrier generated within the depletion region W are separated by the junction field, electrons being collected in the N region and holes in the P region. Now you should understand this, right?
Okay.
Electrons will go to the N side, as I showed. Electrons will go to the N side, holes will go to the P side. Those who are generated in the depletion region. Also, minority carriers generated thermally within a diffusion length of each side of the junction, actually not junction, each side of the depletion layer edge, diffuse to the depletion region and are swept to the other side by the electric field. As I mentioned, in P side within one diffusion length, the electrons which are generated, they may go to the N side by the field. If the junction is uniformly illuminated by photons with h nu greater than Eg and added generation rate GOP EHP per centimeter cube per second participates in the current. Why added generation rate? Because there is already thermal generation rate. Okay. Because of thermal generation, there is a drift current. In addition to that, there will be a optically generated current. Okay. And that optically generated current, because since the illumination is steady state, there is a steady state generation of carriers from optical generation of carriers. Okay, the number of holes created per second within a diffusion length of the transition region on the N side is ALP into GOP. ALP is the volume I mentioned here. ALP is the volume, and multiplied that with that is optical generation rate GOP. So this gives you, GOP is the number of EHPs per cubic centimeter, that means per unit volume per second. So if you multiply that with volume, what do you get? Number of EHPs generated per second. And from those EHPs, actually you need only the what should I say?
Minority
Electrons
carrier.
for N minority carrier. For N side, we need P holes. From P side, we need holes. So ALP GOP is the number of holes created here actually per second because of optical absorption. Okay.
Yes.
So what will be the charge Q into LP GOP, right? Per
Yes, sir.
second. So কোথায় গেল? This one. Similarly, ALN GOP electrons are generated per second within ln of XPO. So that is the number of electrons generated here per second in this region, in this volume. And AW GOP carriers are generated within W. So within the depletion layer, AW into GOP. That is the number of carriers generated within the depletion region. So the resulting current due to the collection of these optically generated carriers by the junction is IOP. So IOP is equal to what? All these multiply, all these added, then multiplied with Q, right?
Yes, sir.
Remember, all these will be added because for hole and for electron, both current direction is same.
Yes, sir.
Holes and electrons are going in the two opposite direction, but current direction is same. That's why all these three components will be additive. So this part, have you understood? Any question?
No, sir.
IOP,
Yes.
optically generated current. So if we call the thermally generated carriers described in the diode equation as I thermal. So this ITH was actually in chapter 5, was denoted by I naught, I0. If you remember the diode equation, I0, e to the power QV by KT minus 1. See, this I0 and I thermal is same actually. Here they have used different representation.
স্যার
Hmm.
আইওপির উপরে কি স্যার এই ফিল্ড যেটা এই ফিল্ডের স্ট্রেংথের কোন ইফেক্ট থাকবে না? ফিল্ডটা কত স্ট্রেংথফুল? আমি যেটা জাস্ট
এটা তো
জেনারেটেড কত
আগেও
ক্যারিয়ার
বলছি। I talked about this. Oh, sorry. I talked about this. There, the current, the thing which matters is number of carriers available
আচ্ছা আচ্ছা আচ্ছা
to travel. Okay.
স্যার এই রিমেম্বার
The field will actually it should have some effect, but that effect is not the determining factor.
ইয়েস
Like I discussed this before. I am sure you remember.
ইয়েস স্যার
So where was I? Yeah, this I thermal and I0, these are equal. And I0, if you remember, this was equal to this QA. It was dP by LP PN plus DN by LN NP, right? In the
Yes.
diode equation. But dP by LP is equal to LP by tau P. Why? dP into tau P is equal to LP square. Remember those things?
ইয়েস স্যার
Hmm? So dP by LP and LP by tau P same thing. Okay, so this part is actually this I0, which is denoted by I thermal here, ITH here. So total the current for illuminated junction is what? This I equal to this. This is the diode equation, first part, minus I op. Why minus I optical? Because this I optical is flowing from N to P side,
ইয়েস স্যার
negative direction. Okay, that's why this I op and this drift current, they have same direction. That's why both are negative, both are minus. Okay,
ইয়েস স্যার
so this I thermal is this, you know, and this IOP is this. So we get this equation. This is the current equation for for an illuminated junction, a junction which has been illuminated by light. Okay,
ইয়েস স্যার
so from here, what can you understand? This part, this first part is typical diode equation. So diode characteristic curve, you know, it looks like this, right?
ইয়েস স্যার
When you illuminate the junction, there is a negative part which is added with this current. Okay, so LP, LN, W, these are actually constant. QA. So GOP is can be variable depending on the intensity of the light. Okay, so because of this part, IOP minus IOP, what will happen in a illuminated junction? The whole IV characteristics will go
Downwards.
down
ইয়েস
by this amount, and this amount is proportional to GOP.
সুন্দর
Understood?
ইয়েস স্যার
So you can understand, if you increase GOP, current will,
ডিক্রিজ
in the negative direction, current will
Increase.
become more and more negative. Okay.
ইয়েস স্যার
Okay. Possible. Others, have you understood this? 139 খালি রেসপন্ড করে, অন্যদের কি
Sir.
অবস্থা? Yes.
স্যার এই যে গ্রাফটা একটা জিওপি গ্রাফটা একটু বুঝাই দেন আরেকবার।
Which part?
স্যার এই যে কারেন্ট জিওপি ভ্যালুটা যে আস্তে আস্তে বাড়ছে।
This is the typical IV characteristics of a diode,
Yes.
non-illuminated diode, a diode
Mhm.
which is not illuminated, right?
Yes, sir.
Once you introduce illumination, this term is added with the diode current.
Yes. আচ্ছা আচ্ছা।
Okay, so
Yes,
this
sir.
part is subtracted actually, negative.
হুম
So this whole curve will go down by this amount.
ওকে
Just like adding a DC value with a curve. Here actually you are subtracting a DC value from the curve. From every point of the curve, you are subtracting this. So this whole curve will go down by this amount.
This amount. Okay, sir.
Okay, so
Yes,
this
sir.
reverse biased region, this region
Mhm.
here, uh, these are the optical, this G1, G2, G3, these are different optical generation rates. G3 is greater than G2, G2 is greater than G1. By varying the intensity of the light, you can vary the optical generation rate, right?
Yes, sir.
Varying
Yes,
intensity
sir.
of light means what? The number of photons you are supplying per second. If
Will be
you
increasing.
change that,
Yes.
GOP will change.
Yes, sir.
Okay. Now
Mhm.
this downward shift of the original curve, this
Yes, sir.
downward shift is by the amount of this, right?
Mhm. Yes, sir.
And this amount is proportional to GOP. Q is
Yep.
constant, A is constant, LP, LN, W, these are fixed valued.
Mhm.
So GOP, this downward shift, this amount, IOP is proportional to GOP.
Yes, sir.
So if you increase GOP, the downward shift of the
Down.
curve will increase.
Yes, sir.
Oh, so okay, here G1 is less than G2, G2 is less than G3. So you can see that if you increase the optical generation rate, the
I
downward
will be
shift
going
will be
down.
more and more. Okay,
Mhm. Yes, sir.
understood?
Yes, sir.
Yes.
Okay. So when the device is short circuited, that means you short circuit this P and N side, that means V will become 0. Remember, this V is in the equation, this V is externally applied voltage, the part of externally applied voltage which appears across the PN junction, right?
Mhm. Yes, sir.
So if you make this 0, how can you make this 0? By short circuiting P and N. So this e to the power QV by KT becomes what?
It is
One.
0.
1. So
One
this
total
first
0.
part
0, 0.
becomes
0.
0. So I is equal to
Minus
IOP. Minus IOP.
minus IOP. So there will be a short circuit current. Remember, in illuminated junction only, there will be a short circuit current from N to P, right? Minus
sir.
IOP. Minus IOP means what? From N to P.
Into.
These directions are important. Okay, keep these things in mind. So when the device is short circuited, that means V equal to 0, the terms from the diode equation cancel. In equation, that means this cancel as expected. However, there is a short circuit current from N to P equal to IOP. Okay. Thus, the IV characteristics of figure 8.1c cross the I-axis at the negative values proportional to GOP. So, for that case also, since this is short circuited, V is 0. Okay. So, what will happen is this only this part, since current is negative, current is flowing, IOP is from N to P side, current is negative, and that current, this I equal to IOP, that means this, so this depends on GOP. So with this current will be negative, so the current will be negative, so this crossing with the V, this crossing will be more and more negative, crossing with the V is 0, right?
Yes, sir.
Yes, sir.
So IOP is the crossing of this IV characteristic with this I axis at that condition, V is 0. So this crossing will be more and more negative, right?
Yes, sir.
Yes.
So that is what is mentioned. Thus, the IV characteristics of figure 8 on C cross the I-axis at negative values proportional to GOP. Okay.
Yes, sir.
Now, when there is an open circuit, now instead of short circuiting, you open this. So if you open this, this current is 0, right?
Yes.
So if this current is 0, you can equate this. So this V is, remember, forward voltage. We have assumed here V is forward voltage. So
Mhm.
this is equal to 0. So from this equation, you can get a value of V.
Mhm. Yes, sir.
That V is open circuit voltage.
Achha.
Okay, so if you equate this equal to 0, what do you get? Actually, I have shown here. So I thermal, this first part equal to IOP.
Mhm.
From there, e to the power, this V becomes VOC, open circuit voltage.
Mhm.
So from there, you get this e to the power Q VOC by KT is equal to IOP by I thermal plus 1. This one will go to this side. So from here, VOC is KT by Q ln of this, right?
Yes, sir.
So this VOC is, this is an interesting thing. For a illuminated junction, if you open the circuit, you will get a voltage across the PN junction, which has the same polarity as the forward bias voltage.
Hmm.
That
Yes, sir.
means P side positive, N side negative.
Yes, sir.
Understood?
Yes, sir.
Remember, these things I am talking about only applicable for illuminated junction. For unilluminated junction, VOC is 0. For unilluminated junction, ISC is 0. Okay. These are the properties of illuminated junction. Only in illuminated junctions you will get this VOC, and when V equal to 0, you will get a ISC, short circuit current, which is IOP.
Sir, this is also an equilibrium scenario, right? Sir, open
Not
circuit.
equilibrium. This is a steady state.
Oh, sorry, a steady state.
Steady state, yeah.
Steady state
Steady
scenario.
state is not equilibrium. It's
Yeah,
unequilibrium.
unequal.
So once so VOC is equal to KT by Q ln of IOP by I thermal plus 1. The same equation I showed here. This equation. Now we'll simplify this equation a little bit. IOP is what? This Q into Q কোথায় গেল? দূর। QA GOP ln LP plus ln plus W, right? And I thermal is this part actually. QA LP by tau P PN plus ln by tau N NP. This part. So this divided by this IOP divided by I thermal, QA will cancel. Right? So there will be GOP into this divided by this part. LP by tau P PN plus ln by tau N NP. Right?
Yes.
So this KT by Q ln LAP plus ln plus W into GOP divided by LP by tau P PN plus ln by tau N NP. Okay, plus 1. So up to this, okay.
Sir, ln plus LP plus W এটা লন এর ভিতরে ঢুকলো কিভাবে? ডিভাইডেড বাই থাকার কারণে।
এটা তো হচ্ছে ln IP by I
আচ্ছা ওইখানে ভাগ করছেন। আচ্ছা ঠিক আছে।
I have just put the value of IOP. IOP is QA into this.
Okay, sir.
And I thermal is QA into this. Oh, sorry, IOP is QA GOP into this. Okay, and I thermal is QA into this. So QA cancels from numerator and denominator, only GOP remains, and these terms remain.
Okay, sir.
So further simplification, VOC equal to KT by Q ln. Oh, for a special case, symmetrical junction, PN is equal to NP. PN is equal to NP means minority carrier concentration at N side and P side are same. Okay, that is easily obtainable if the doping concentration of P side and N sides are same. Then majority carrier concentration same, so minority carrier concentration will also be same. Right?
Yes, sir.
And recombination lifetime is actually depends on carrier concentration. Okay. So for a symmetrical junction, Pn equal to Np and tau P equal to tau N, we can rewrite this equation. So we will put here, instead of tau P, we will put tau N, and instead of Np, we will put here Pn. So Pn by tau N is common here. Pn by tau N, right?
Yes, sir.
So Pn by tau N, from the denominator we will take Pn by tau N common. So same equation here, only Pn by tau N I have taken common. So that will leave us with LP plus Ln. Pn by tau N into LP plus Ln into GOP, right?
Yes, sir.
Plus 1. So Pn by tau N again is the equilibrium generation recombination rate.
Pn by
tau N. Minority carrier, of course, minority carrier recombination.
And thermal generation rate?
Yeah, definitely. Yeah.
Thermal. Yes.
Pn is the equilibrium, thermal equilibrium concentration, minority carrier concentration, right? So on average, Pn will recombine within tau n time, and same amount of Pn will be generated within that tau n time, right?
Yes, sir.
So Pn by tau n is the thermal equilibrium thermal generation rate or recombination rate, same, both are same. So that is denoted by G thermal. Okay, so here this Pn by tau n is G thermal, so GOP by G thermal, and here actually W has been ignored to cancel actually numerator, to do simplification, cancel the numerator and denominator. So neglecting generation within W.
স্যার
Okay,
এটা কিন্তু
this
স্যার নরমাল ক্ষেত্রে আমরা নেগলেক্ট করি, মানে আমরা কিন্তু হোল কনসেন্ট্রেশন এক পাশে আর আরেক পাশে করি, বাট জেনারেশন রেট কিন্তু ডিপ্লেশন রিজনে হইতে থাকে স্যার কন্টিনিউয়াস।
depletion region in definitely within the depletion region there will be generation, definitely, most definitely.
স্যার ওটা স্যার নরমাল পি
They
ইনজাংশন
are
আলোচনা আমরা ইগনোর করে গেছি।
mhm.
নরমাল পি ইনজাংশনের জেনারেশনের ক্ষেত্রে যখন আলোচনা করছিলাম তখন রিভার্স কারেন্টে স্যার ওই টুকু পার্টের মাইনরিটি ক্যারিয়ার নেই ওখানে কনস্ট্যান্ট ধরে গেছে।
Yeah, we ignored it. But here actually generation comes from, this generation comes from optical generation.
Yes,
There was no optical generation, there was only thermal generation.
yes, sir.
Okay, this W comes from the contribution of optical generation, and there can be significant optical generation in the depletion layer, but they still in the book they have ignored it again, as far as I can understand, just to make the equation simple. The objective is to give you an idea about how VOC varies with this generation rate, optical generation rate and thermal generation rate. That's why they are doing this simplification. So if we ignore the generation within W, that means if we ignore this W part, then ln plus lp will cancel from numerator and denominator, right?
Yes,
So
sir.
we'll get kT by q ln GOP by G thermal plus 1. Again, GOP may be much greater than G thermal. This GOP much greater than. That is practical, I would say, because you can see here this reverse current is because of the original diode current. Reverse current is due to thermal generation, right?
Yes,
But
sir.
optical generation can be significant, much greater than this thermal generation rate. So GOP much greater than G thermal, that is practical. So if GOP is much greater than G thermal, then this GOP by G thermal is much greater than 1.
Yes, sir.
Right? So
Yes,
we
sir,
can
we can
ignore
do.
this one again. Simplification, just simplification. So this becomes KT by Q ln GOP by G thermal, G optical by G thermal, right?
Okay, sir.
So from here, the objective is to show you how again things varies. So it may seem VOC is almost this, or this equation actually. Let's come back here. VOC is KT by Q ln GOP by G thermal. So it may seem that if you increase GOP indefinitely, VOC will also increase indefinitely.
তাই তো দেখা যাচ্ছে।
Right?
Yes, sir. It seems like that.
It seems like that. And what is VOC? Polarity of VOC is just like the polarity
Positive
of
bias
forward
voltage.
bias voltage.
Yes, sir.
Okay. So by increasing optical generation rate, we can get a voltage, open circuit voltage across the junction, which can be increased. But that is actually not the case, because as you increase GOP, the carrier concentration will increase.
Yes, sir.
So if the carrier concentration increase, recombination lifetime, remember recombination rate depends on what? Number of available carriers
and holes. Yes, sir.
electrons and holes. So if electrons and holes increases, recombination rate increases.
Yes, sir.
Right? So recombination lifetime, what happens to recombination lifetime?
It gets decreased, and at the same time the length will get decreased. Recombination length.
Okay, well, let's not go to length. Recombination lifetime will decrease. Okay, recombination lifetime decrease, that means tau n will decrease.
Yes, sir.
So what will happen to Z thermal?
কোনটা স্যার? জি
There,
থার্মাল।
Pn by tau n is Z thermal.
জি থার্মাল বাড়তে থাকবে স্যার।
Z thermal will also increase. So
Increase.
if you increase GOP, VOC will increase a bit, of course, but at some point G thermal will also increase, and by increasing GOP, you will not be able to increase GOC a lot. Actually, from common sense, you can understand, since this is the forward voltage, this is equivalent to a forward voltage. What is the maximum value of forward voltage you can get across a PN?
0.7, 0.8 এরকম।
VO,
VO,
the contact potential.
contact potential.
Okay, so the maximum limit of VOC is VO. Understood?
Yes, sir.
So actually the term G thermal equal to Pn by tau n represents the equilibrium thermal generation recombination rate. As the minority carrier concentration is increased by optical generation of EHPs, the lifetime tau n becomes shorter and Pn by tau n becomes larger, since Pn is fixed. Pn is the equilibrium minority carrier concentration. Therefore, VOC cannot increase indefinitely with increased generation rate, right? This
Yes,
thing
sir.
should be clear now. In fact, the limit of VOC is the equilibrium contact potential VO. This result is to be expected since the contact potential is the maximum forward bias that can appear across a junction. Okay.
Yes, sir.
The appearance of a forward voltage, again, forward voltage across an illuminated junction is known as photovoltaic effect. So this creation of VOC, forward voltage, again, forward voltage due to illumination of a PN junction, this is called photovoltaic effect. So up to this, any question, first of all? Understood?
No,
So here you can understand, when we short the photodiode, illuminated photodiode, we have a short circuit current, and that current depends on GOP,
illumination. Yes.
illumination level. So this scenario is useful when you want to get a photo detector. You want to detect the presence of light, or you want to detect the variation of light intensity. That is photo detector. So where this is shorted, this application, sorry, this scenario is useful for application as a photo detector. Same photodiode. This photodiode can be used as a photo detector when this is shorted. Actually, you cannot short it. You have to put a register here. Understood?
Yes, sir.
And when you open this, you get a voltage, which is photovoltaic effect. The voltage magnitude is small. That's different thing, but you will get a voltage, illuminated junction. So this is useful when you want to use the photodiode as a battery, solar cell. Okay, so same photodiode can be used, different configuration, of course, can be used as a photo detector, or it can be used as a battery, solar cell.
Yes.
Okay, so these things have been shown in the following diagram. I will show you. Depending on the intended application, the photodiode can be operated in either third or fourth quarters of its IV characteristics. So that I will show you here. So here this has been shown. So this is equilibrium with unilluminated junction, shorted, no, sorry, open, and this is illuminated junction, open. So when VOC is created, since VOC is has same polarity as the forward voltage, when VOC is created, the Fermi levels of both sides will be misaligned by this QVOC, just like a forward biased PN junction, right?
Yes.
So you can see here that just like forward biased PN junction, the maximum value of VOC can be this VO. Now this different intended application, this figure shows. Remember, in the IV characteristic, third quadrant does, sorry, second quadrant, there is no point in the second quadrant. Okay.
Yes, sir.
In all these figures, you can see these are illuminated junctions. All these three junctions are illuminated junctions. So the IV characteristics, the regular IV characteristics of a diode has been downshifted by some amount, right?
Yes.
In both of the in all of these three cases. Is it clear?
Yes, sir.
So IV characteristics of the diode, illuminated diode or photodiode, has points in the first quadrant, third quadrant, fourth quadrant. There is no point in the second quadrant, right?
Yes, sir.
So
Yes.
first quadrant operation, if you forward bias the PN junction, of course you have to put a current limiting resistor. Forward bias a PN junction, current will be positive. From P to N is the positive current. The portion of this external voltage appearing across this forward bias PN junction is V, which will have polarity plus on the P side, minus on the N side, right? This is the
Yes, sir.
forward polarity of the forward voltage. So forward voltage, so here current is entering the positive terminal and leaving the negative terminal. First quadrant operation. So this point will be on the first quadrant portion of the IV characteristic. There is a point shown here, right? You can see.
Mhm.
So in this case, current is entering the positive terminal, leaving the negative terminal. So what kind of element is this in this case?
Passive element.
This is active element.
Passive element. Energy
Passive element, exactly. So this device is absorbing or
power.
consuming power from the external circuit. So this is first quadrant operation. Diode is forward biased. Understood?
Yes, sir.
Yes, sir.
But this forward biased operation actually is not used. Reverse bias is preferred. This is reverse bias case. So PN junction is reverse bias. So current is flowing in the opposite direction. This current is uh, drift current, drift component of current plus the optical generation current, optically generated current, IOP, right? But the direction is from N to P, negative. And the portion of E appearing across this PN junction, that will have polarity VR, that will have polarity VR positive on the N side and negative on the P side, right?
Mhm.
Reverse bias voltage. So voltage is negative, current is negative.
Mhm.
Okay, remember this current P to N is considered positive, this polarity of voltage is considered positive. So this current, this voltage, both are negative. So the operation is in third quadrant, current negative, voltage negative.
Mhm.
Okay, but
Yes, sir.
in this case also current is entering the positive terminal
Passive order.
and leaving the negative
Negative.
terminal. So this element is acting as a
Passive element.
passive
Yes.
element. So here also the device is absorbing power from the
Source. From
external
light.
circuit. Okay,
Yes, sir.
Yes, sir.
so both first quadrant and second quadrant operation, the device is
Ah,
acting as a passive element absorbing energy from the external circuit, but the third quadrant operation is preferred, and this is this quadrant operation is actually useful as a photo detector when you want to use diode as a photo detector. As you can understand, this reverse current, this is directly related to, or you can say directly proportional to the optical generation rate, as I have already showed you above. This reverse current, right?
yes, sir.
This reverse current, this much, this directly depends on optical gen GOP. So as a photo detector, you can use the photodiode as a photo detector when you operate it in third quadrant. Now, very interesting. Fourth quadrant operation. This is possible only for an illuminated junction. For unilluminated junction, there is no portion of the IV characteristics in the fourth quadrant. Okay.
Mhm.
So fourth quadrant operation, this junction, when you open circuit this junction, there is a an illuminated, there is a open circuit voltage. That voltage polarity is what? Plus on
Positive
the
to
P
negative.
side, minus on the N side.
Hmm.
Now you connect P and N, of course, through a resistor. then what will happen?
Current will flow from P to N through that wire.
Exactly, current will flow.
From P to N through that wire.
No, current will flow from what?
Sir, P থেকে N wire দিয়ে যাবে
YP to N.
স্যার পি এ পজিটিভ হাই ভোল্টেজ স্যার রেজিস্টার পয়েন্ট অফ ভিউ থেকে যদি দেখি রেজিস্টারের হাই ভোল্টেজ পজিটিভ আছে
রেজিস্টার পয়েন্ট অফ ভিউ থেকে দেখা যাবে না, কারেন্ট আসবে কোথা থেকে?
আচ্ছা ভিতরে জেনারেটর স্যার ওটা যদি সেল হিসাবে কল্পনা করি সেলের ভিতর তো এন থেকে পিতে যাবে বাট সেলের বাইরে পি থেকে এনে যাবে মানে আমি বললাম ওয়্যার দিয়ে আর হ্যাঁ
হ্যাঁ, from where P to N, exactly. Through
Inside
PN
the battery,
junction, it
it
will go from N to P.
N to P yes ব্যাটারিতে এন থেকে
Okay, because this is optical generated current.
জি স্যার ব্যাটারি হিসাবে কথা বলছি।
So here you can see current is entering the negative terminal. Current is negative. Current is negative, voltage is positive. So which quadrant operation?
It's fourth
Fourth quadrant. Voltage positive, current negative.
Hmm.
And the current is entering negative terminal, leaving positive terminal. So this device is acting as a battery.
yes sir.
So this device is supplying energy or supplying power to the external circuit. So fourth quadrant operation is required when you want to use this as solar cell, as a battery. Okay,
Yes sir.
understood. So that is what is mentioned here. Notice that in the fourth quadrant, the current flows from the negative side of V to the positive side as in a battery. Okay, so in this case, power is delivered from the junction to the external circuit. So if power is to be extracted from the device, the fourth quadrant is used. On the other hand, in applications as photodetector, we usually reverse bias the junction and operate in the third quadrant. Why reverse bias the junction? When I discuss photodetector, you will see. Okay. Reverse biasing the junction will increase the sensitivity of the photo detection. So up to this today, so photodiode, same photodiode can be used as a photodetector or solar cell. Next class, I will talk about solar cell, and then after solar cell photodetector, then light emitting diode, then laser, and those will be all. So photodetector, then LED, light emitting diode, and laser. This is laser. So there, and up to this will be the syllabus to the end of laser. There is less math in this chapter, mostly description. So I believe this chapter will be easier for you than the other chapters.
স্যার
Okay.
ম্যাথই সহজ স্যার
Mm-hmm.
ম্যাথ পরীক্ষার হলে করা সহজ স্যার মানে ডিসক্রিপটিভ পার্ট কোনটা লিখে কোনটা লিখবো
Derivation, there is almost no derivation, very small derivation, mostly description here in this chapter. So any question on today's class?
No sir.
Okay, then I will take the attendance. Let's stop recording.